So welcome to the fourth video in special relativity. In this video, we'll be looking at the concept of simultaneity under relativistic conditions. So simultaneity we say that two events are simultaneous in an inertial reference frame if the light signals for those events reach an observer located halfway between the events at the same time. And so to know if two events are simultaneous, we need to know that two observers in the same reference frame, but at different locations within that reference frame, are measuring the same time. That is, we need to know that the clocks of those two observers are synchronized. So we'll have a look at how we would do that using our space-time diagrams. So first we'll have a look at what we're calling our stationary reference frame. So that is, this is the reference frame from the point of view of the man, and from his point of view, he's stationary. We have one person and he's located at time t equals 0 at the position x equals 0. He's not moving through space, he's only moving through time. So his world line is vertical. And we want to know how we would synchronize the clocks between him and another point in space in his reference frame. So we'll put in a second observer and we'll put him at a distance of 1 light year away, also at the time t equals 0. And this second observer's world line is also vertical. He's not moving through space relative to our first observer. He's in the same reference frame. He's just moving through time. So for these two people to tell if the events they saw were simultaneous, they need to know that they're measuring the same time. So we need to be able to synchronize the clocks of these two observers. And the way that we can do this is as follows. So if we say person 1, located at x equals 0, sends out a light pulse to person 2. We know the light pulse is moving at the speed of light, at c, and so we can draw that in our diagram as a line with a gradient of 1. So that line is 45 degrees to our axis of our stationary reference frame. So that is, it moves with a speed of 3 times 10 to the 8 meters per second, and after 1 second, therefore, it's moved 3 times 10 to the 8 meters. When the light beam reaches person 2, he records the time, so we say 6 p.m, and immediately reflects it back to person 1 with a timestamp on it. When person 1 receives that light pulse back, he knows that at half the time between when he sent it and received it, it was 6 p.m. So he sets his clock such that it would have read 6 p.m. at that point in time. And so those two clocks are now synchronized. Now I'll just take a little bit of time out here to explain the directions of the reflected rays. So light is traveling at the speed of light at c, so the gradient of the path of the light through space and time on this diagram must always be 1. And that's how we set it up, by making our y-axis equal to ct. If the light is traveling forwards through space, so that is in this case if it's going from x equals 0 to x equals 1 in our reference frame, then it will have a gradient of +1. And if the light is traveling backwards, so for example from x equals 1 back to x equals 0, it will have a gradient of -1. And so that's how we get the world lines for the light in both directions. Okay, so now we know how two observers in their reference frame can synchronize their clocks. And so we'll switch to having a look at what would happen from the people traveling in the rocket at some speed v, from their point of view. So from the point of view of an observer sitting on the rocket, that's the reference frame of the rocket. And we'll set it up the same. We have one rocket, which is at time t equals 0, located at x equals 0. From his point of view, he's stationary. So he's not moving through space, he's only moving in time, and so his world line is vertical. We'll put our second rocket-based observer, again at a distance of 1 light meter away, at time t equals 0. And him also, he's not moving through space either, he's moving at the same relative velocity as the first rocket, so his world line is also vertical. They then synchronize their clocks in exactly the same way as our blue men. So rocket 1 sends out a light pulse. When the light beam reaches person 2, he records the time, timestamps the light beam and sends it straight back to person 2. And we imagine he does this with no delay at all. When person 1 receives the light pulse back, he knows that at half the time between when he sent it and received it, it was 6 o'clock. So he sets his clock such that that was the case and the clocks are synchronized. The interesting question now is how would our blue people, from their reference frame, their stationary reference frame, see what's happening to the people on the rockets. So to do that, we'll put both our blue men and our rockets on the same diagram. So this is the diagram from the reference frame of the blue men. We know that the world lines of our two men are vertical. They're not moving through space. From their point of view, they're stationary. And from our very first look into space-time diagrams in the previous video, we know that the world line of our rocket moving with the... And from our very first space-time diagrams in the previous video, we know that the world line of our rocket moving with a velocity v and starting at x equals 0 from the time t equals 0 will look like this. And we know that our second rocket, which started at time t equals 0, but started at a location 1 light meter in front of the first, and is moving with exactly the same speed as the first, will then look like this. So our men see these rockets zoom past at a velocity v. At time t equals 0, we will say that our men and our rockets are in the same location. So man 1 and rocket 1 send out their light beams from the point x equals 0. The light beams travel to man 2 and rocket 2. Man 2 and rocket 2 then reflect their light beams back to man 1, rocket 1 with the timestamp. So before we discuss that, I'm just going to make another short comment on the direction of the light beam. So if we look at the direction of the light beam coming from rocket 2 back to rocket 1, it doesn't seem to gel. And the reason I think, is because we're used to seeing light reflected from mirrors, and we're used to thinking that the angle of incidence should be the same as the angle of reflection. In this case, we're not looking at light moving just through space, but we're looking at light moving through space-time. And we know that on this diagram, the gradient of light must be plus or minus 1. So, to the blue men, they've already sent and received their beam and synchronized their clocks before rocket 2 receives the original beam from rocket 1. And once again, rocket 2 records the time that he received the light beam. Again, we'll say that it was 6 p.m. and sends it back to rocket 1. And rocket 1 receives the beam at CT equals 3. So half the travel time of the light is at CT equals 1.5. So to the men in the rocket, these 2 points here are synchronized. Their clocks read the same time. But to the blue men, CT equals 1.5 is here. And from their point of view then, they think that these 2 points, these 2 light green crosses, should be synchronized. So they think that the clocks at these 2 points should read the same time. And now this is one of the more strange concepts of relativity. That is that simultaneity is relative. So whether or not 2 observers agree that the events occur at the same time really does depend on how fast they're going relative to each other. So this is one of the first pieces of strangeness that we can add to our knowledge bank of special relativity. And this piece of information also gives us a little more information on how we can use our space-time diagrams.